I will explain you some basic fundamentals for the design of RC footing. They are as per IS 456-2000. For the designing of RC footing, our first step is to determine the size of footing. Column is given in a square shape. The footing should be adopted square, and if the column is rectangle, the footing should be adopted rectangle. If the footing shape is rectangle, you can see in the diagram, if we adopt the shape is rectangle, then we have to consider the length and width of the footing, such as the cantilever portion in both directions should be equal. So you can see in the diagram, if I am considering this is the length and this is the width of the footing, then the remaining portion in cantilever, let's say I am showing here with the x distance, x in this dimension is in longer direction and the x distance in the wider direction, both are same. Okay, so here my x value both should be same. The soil bearing capacity is behaving as a stress from the soil on the footing. As we know that the stress is resisting force on a particular area, and we know that the stress is equal to force upon area, so that we can determine the provided area for the footing, that is the total force acting on the footing upon soil bearing capacity. When we design any type of footing, we generally have the value of soil bearing capacity, and we can determine our area for the footing. Next step is to determine the net upward pressure. It is very necessary to determine the net upward pressure, as in the whatever pressure coming from the soil on the footing, and that will be from the downward to upward direction. You can see in the diagram, here is the plan diagram for the footing, okay, and these are the pressure distribution diagram from the soil, which is from the downward to upward direction. You can see I am showing the arrow from downward to upward direction. Maximum pressure, we have a formula that force upon area plus the moment about x upon z, z as in section modulus for the particular of the footing, plus moment about z upon section modulus about z direction. The unfactored maximum pressure should be less than SBC, and if this is more than SBC, then the foundation will be fail. P minimum, the minimum upward pressure should be more than 0. If P minimum is less than 0, the footing will be uplift and it will be fail. This particular diagram will happen only when you are having eccentric footing. When the footing is subjected with only axial pressure, then you can find the uniform distribution of the soil pressure. The moment about x and moment about z both are 0, and then my net upward pressure value will be only P by A. Okay, now let's see the step number 3. To determine the maximum bending moment, we can determine our maximum bending moment at the face of the column. Okay, so you can see the distance x, which consider as a cantilever, or we can see the lever arm portion which act as a cantilever. Okay, and the maximum bending moment for the cantilever is WL square by 2. My length is here, I am considering x, so it will be WX square by 2. Our next step is to determine the depth of footing. With the help of maximum bending moment, we can calculate the total depth and effective depth of the footing. If the depth of footing is less than 300 mm, the design may fail in shear. To avoid for providing shear reinforcement in footing, generally we take the sufficient depth so that our foundation will not fail in shear. Next step is the reinforcement in both direction. We generally provide reinforcement and we consider as a main reinforcement for the both direction. As per IS 456 clause number 26.5.2.1, if we are using Fe 250 as in mild steel, the percentage of reinforcement is 0.15, and this is a clause for the minimum reinforcement. And if we are using Fe 415 as in HYSD steel bars, the percentage of reinforcement is 0.12%. Next step is we have to check one-way shear. The one-way shear in footing should be checked at a critical section. The critical section for the one-way shear is at the depth D from the face of the column. You can see in the diagram, here is a plan diagram for the footing, okay, and here is a face of column, okay, and
here is a depth d distance. We already determined effective depth d. So we just deduct depth d from particular lever arm in the horizontal or we can say in longitudinal direction. So whatever dotted line is the critical section for the one-way shear, and we can determine our one-way shear check for the both direction, in longitudinal direction and in transverse direction. If the depth of footing is insufficient, it may fail in one-way shear, and if the foundation is fail in one-way shear, the cantilever portion will get uplift and your foundation may fail. Okay. Generally, shear check, we have to check the relation between tau E and tau C. Tau E is less than tau C and the shear check is correct. There is no need to change the depth and the reinforcement of the footing. We can use a formula for tau E is VU upon BD, where my VU is a shear force for the critical section for one-way shear. Okay, here my one-way shear critical section you can see. So we have to determine shear force for this particular section. Okay, it is along y direction, and if we are talking in terms of along x direction, we have to check shear for this particular section. Okay, now if we have varying depth for both the direction, if we have different effective depth for the along x direction also and along y direction also, generally this kind of change we can see when our shape of the footing is rectangle, then my depth y direction and depth in x direction both are varying. Okay, so for the varying depth, we can use clause number 40.1.1 from IS 456-2000. There is a formula given, determine tau E with this particular formula, and we can calculate tau C with the help of provided percentage of reinforcement. We can determine the value of tau C from table number 19 IS 456-2000. Next step is to calculate two-way shear. Two-way shear is checked at a peripheral d/2 distance from the face of the column. You can see here is a plan diagram of a footing. The face of the column you can see here. Okay, and I am taking d/2 from all four sides and the peripheral distance from the face of the column. So here this pink line consider as a peripheral length. In this particular remaining area, we have to determine shear force. Okay, two-way shear is also considered as punching shear. Here is also to check our two-way shear, tau is less than tau C, and then only my two-way shear is correct. Then we don't need to change our depth and the reinforcement of the footing. We can consider the value of tau E is VU upon B0. Here the difference is, what is B0? B0 is resisting length for the two-way shear. The resisting length for the two-way shear here is a peripheral length. Okay, so we have to determine the value, this complete pink line in terms of length. Remember, this is in terms of length, not the area. Okay, and D as in effective depth. Change here for the tau C formula is, we can use the tau C formula for clause number 36.6.3.1 from IS 456-2000. We can use tau C dash. So here we have to determine tau C should be less than tau C dash. So what is tau C dash here? Which is Ks multiplied by tau C, where Ks is 0.5 plus beta of C. What is beta of C? Is a ratio of shorter dimension to the longer dimension of the column. So your beta C is depending on the size of column. It should not more than 1, because if my column will be square, then beta C will be 1. Okay, and the value of tau C is 0.25 under root FCK, and we can compare the relation and we can compare the value of tau E should be less than tau C.